So let's do the mathematical analysis. Now, as I said earlier on, the message signal M of t is any signal, right? It can be any signal. So mostly represented by M of t. And this M of t can also be described as equation of AM cos omega mt, where AM is the amplitude of the message that you are transmitting, and omega m is the angular frequency of the message that you are transmitting. And then the carrier signal, which is CT. Let me get this. C of t is equal to AC cos omega mt. These are the two information that we need. And based on this block diagram, you can see that we are going through a summer. And therefore, we can say that our input, which is V1 of t, as illustrated over here, is going to be equal to our message signal plus our carrier signal, which is going into the modulator, which is the nonlinear device in this case. And as I said earlier on, the message can be any signal, and therefore we can leave the M of t like this and then expand our carrier signal, which is AC cos omega ct. This is equation 1. Now let's look at our output. We are passing this input into the nonlinear device and we are expecting this output. And since the square law, I explained this earlier, that we are going to get the output in this format: A1 V1 of t plus A2 V1 square of t. So in this case, we have V1 of t and V1 square of t, and we have V1 of t equal to M of t plus AC cos omega ct. We can actually substitute. So if we make this one equation 2, we can actually substitute the equation 1 into equation 2, of which we are going to get V naught of t to be equal to A1 into brackets M of t plus AC cos omega ct plus A2 into brackets M of t plus AC cos omega ct all squared. Now the rest is just algebra. We just need to simplify everything and then see where we are going to arrive at. So the most important part that we want to simplify first will be the right hand side, and then in doing that we are going to simplify that one before we combine to the main equation. So let's do that here. A2 into brackets M of t plus AC cos omega ct multiplying by another M of t plus AC cos omega ct. Right? We are expanding the right hand side on this one. So in doing this, when you multiply it through, we are going to get M square of t plus 2 M of t AC cos omega ct plus AC squared cos squared omega ct. Maybe some people may be confused, so let me go one after the other. This one was multiplied by this. I got M squared of t. It was also multiplied by this. This one multiplied by this again. You get M of t AC cos omega ct. And then we are done with the other side. We pick this one as well. So AC multiplied by AM is also equal to M of t AC cos omega ct, of which when we add them, we are going to get 2 M of t AC cos omega ct. But you know that AC cos omega ct multiplying another AC cos omega ct is going to give us AC squared cos squared omega ct. So in that way, we can multiply truth by the A2 and we are going to get another form of equation, which is equal to a2 m square of t plus 2a2 m of t ac cos omega ct plus a2 ac squared cos squared omega ct. Now substitute the expansion into the main equation up there. We are going to get, expanding the left hand side as well, we are going to get a1 m of t plus ac cos, or let's say a1 ac, a1 ac cos omega ct plus a2 m2 of t plus 2a2 m of t ac cos omega ct plus a2 ac squared cos squared omega ct. This is the output, or let me replace this one so that you really understand it. This is the output V naught of the nonlinear device, and as you can see, whatever we passed through the nonlinear device, we didn't get the exact thing because of the nonlinear nature of this nonlinear device. We encountered some sort of harmonics, which is the integral multiple of whatever was placed in, and therefore you can observe it yourself that there has been some noise being generated in addition with our main modulated signal, and therefore we need this thing to be passed through band pass filter. So in passing it through the band pass filter, this is going to be the output is going to be our input, and then at the end of the day we are going to get our S of t. And our band pass filter, remember, that's going to take a range of values, which means that some part with a very low frequency, they are not going to be part of the final equation. Some part of a very low frequency are not going to be part of the final equation. So as you can see here, as you can see here, this A1 m of t will go out because it will be having a very low frequency range. It's not being carried by the carrier frequency of which the carrier signal of which we are using to modulate that message signal, so it will go out. You get me? We are doing modulation, and therefore we are using the carrier signal to modulate our message signal. And at the end of the day, after passing it through the nonlinear device, we realize that some part of the message signal has not been modulated, of which is going to be exposed to a lot of noise and other stuff, right? And therefore it goes out. You can see that A1 AC cos omega CT, it's our carrier signal inside, and it also exhibits the characteristics of the input that we place in, so we leave it. We look at this one, we can see that our message signal has been doubled, it has been squared. So this is one of the harmonics effects, and therefore it also goes out. The next one, you can see that we have our carrier signal, all right, we have also a message signal, all right, we have a carrier amplitude, all right, and therefore we have some gain, and therefore we leave this one as well. And then we look at the last one, you can see that our carrier signal has been, our carrier amplitude has been squared, and then even the cos itself, the function itself has also been squared, which is in terms give us a very high frequency, which is also non-needed, is not needed, and therefore this band pass filter, when we pass it through it is also attenuated. So in all, this band pass filter is going to attenuate this first one, is going to attenuate this second one, is going to attenuate this last one, and at the end of the day, our S of t, our net output of the band pass filter is going to be equal to 2a to m of t AC cos omega ct plus A1 AC cos omega ct. This at the end of the day what we are going to get. At the end of the day, this is what we are going to get. And without wasting much time, we can factorize some variables outside. So we are going to get equal to AC A1 can come outside, or let me do it this way so that you get it very well. Cos omega ct outside into bracket 1 plus 2a2 m of t, right? M of t AC, M of t AC, not the AC has been factorized out, so M of t over A1. Remember that there's no A1 component here, so if I'm factorizing A1 out, I need to bring some down here. This is what the simplification will be, how the simplification will be, and then my final expression, we can make it as AC A1 into brackets 1 plus 2A2 over A1, 2A2 A1 M of t, and then cos omega ct. So this expression is the general form of the AM wave, and these are all constants, so we assume that this is equal to AC A1 is equal to AC, assuming A1 is equal to 1 since they are constant. So in that case, I can also represent that one as AC into bracket 1 plus 2A2 over A1 M of t, and then cos omega ct. So remember the equation that we dealt with the other time in my previous video. We saw something as AM over AC, which is equal to M, which is our modulation index, and in this case this becomes our modulation index, which is what, 2A2 over A1, where A2 over A1 are all constants, or gain, some gain, right, which is equal to M. So in that case, or we can also represent as K naught. In that case, we can represent as K naught, and therefore the equation can also be written as AC into brackets 1 plus K naught M of t cos omega ct. So this is basically the overall expression of AM wave signal. So looking at this equation that we have here, let's see the one that we were dealing with the other time. This is the equation that we were dealing with the other time. This is equal to AC into bracket 1 plus AM over AC cos omega t cos omega ct. This is the main equation, and you can see that this is modulation index. When we represent it by K naught, we are going to represent, we get K naught cos omega mt. And the same thing, remember that here we have mt, and we know that our mt is equal to what? Cos omega mt, which is AM cos omega mt. You get me? And for that matter, we are going to actually substitute inside, and you get AC into bracket 1 plus K naught AM, and then cos omega mt, and then another cos omega ct. So you can see that they are all the same. They are all the same, right? So this is the square law method of generating an AM wave. So to conclude this tutorial, I would like to summarize everything about square law. As I said earlier on, in using square law method in generating an AM signal, we need two signals, which are the message and the carrier signal. So the message is M of t, and the carrier signal C of t. This combined signal M of t plus C of t are being passed through a modulator or a modulating device, which is in this case the nonlinear device, which is going to modulate our input signal to an output signal f naught of t. And because of the harmonic nature of the nonlinear device, there are going to be an extra terms being generated in addition to our original signal, and therefore we need to pass it through a band pass filter. After passing it through a band pass filter, this band pass filter is going to attenuate all the unnecessary or unwanted noise, leaving the original one that we need, and therefore that's going to be our output S of t. And this output S of t, it's our general AM wave. So thank you for watching, and see you in my next tutorial.